next talk is enhancing a hierarchical graph and writing language based on MELL elimination, and the speaker is Kento.
Hello, I'm Kento Takyu. Thank you for the introduction. The main topic of our work is hierarchical graph rewriting. Hierarchical graph rewriting is an expressive formalism that subsumes many other formalisms, including term rewriting, process calculus, and so on. However, designing a practical high-level declarative language based on hierarchical graph rewriting is still a challenge. In particular, the right construct for graph cloning and deletion is highly non-trivial. In this work, we propose the graph cloning and deletion constructs for LMNtal, which is a concrete programming language for hierarchical graph rewriting. Our design is based on MELL proofnets, which is hierarchical graph rewriting independently developed for linear logic. Hierarchical graphs support two structuring mechanisms, connectivity and hierarchy. For example, in organizational chart, connectivity represents who manage which group, and hierarchy represents the grouping of member and the nesting of groups. Connectivity and hierarchy can be found also in system configuration diagram and data structure. When we abstract these structures, all structures can be considered with graph structure with possibly with box structure. Hierarchical graphs are graphs with boxes, and it can represent all these structures. LMNtal is a hierarchical graph rewriting language inspired by concurrent logic languages and constraint handling rules. In LMNtal, graph nodes are represented as atomic formulas, and links are represented as zero assignment logical variables. Our implementation of LMNtal comes with a parallel model checker with state space visualizer. MELL proofnets are a graph representation of MELL proofs. And MELL stands for a multiplicative exponential linear logic, which is a practical sublogic for linear logic. In MELL cut elimination, in MELL proofnets, cut elimination is expressed as hierarchical graph rewriting rules, and some rules clone or delete hierarchical graphs. Here is an example of cut elimination rules. This rule for MEL sequence calculus is translated into this hierarchical graph rewriting rules, which clones the box structures. So, cut elimination of MEL proofnets could be provide a useful design. Our main contribution is threefold. Firstly, we extended LMNtal with process context aggregates and designed and implemented the MELL API for graph cloning and deletion constructs. Secondly, we showed that MEL proofnets and their cut elimination rules can be directly encoded into LMNtal. Thirdly, we encoded several process calculi and demonstrated the generality of LMNtal with the proposed constructs. Now I move on to the explanation of LMNtal. There are two approaches to definition of hierarchical graph rewriting. One is a traditional algebraic approach, which views pushout in category theory. The other is a programming language style approach, which is defined with abstract syntax and small step semantics. A comparison of hierarchical graph rewriting system is as shown in this table. Most systems are proposed as models. In contrast, LMNtal is a hierarchical graph rewriting language with PL style definition. I'll explain the syntax of LMNtal. The main construct of LMNtal is named process with historical reason. a process allows no an atom with ordered lengths, parallel composition. Sorry, a membrane which stands for box, or rule for subgraph rewriting. Graph is fixed IT nodes like these, often called port graphs. Process template appears on both sides of subgraph rewriting rule. And process templates allow this hierarchical graph structure and the wildcards, which use the pattern matching of subgraphs named process context. The argument of the process context specify what free link name may or must occur. The left side of the argument represents explicit free links, and the right side of the argument represents whether there can be other unspecified free links. In this presentation, figure is blue boxes show the elemental graph, which correspond to the elemental code below. In this left-hand figure, there are I, A, and B atoms inside the membrane, and 2 G atoms outside the membrane, each connected by links of the same name written in capital letters. A link name occurring once, like this B, named is called a free link, which remain unconnected. Free links played key roles in subgraph matching and rewriting. Some atoms like A and B are drawn as arrowheads. The arrowhead indicates the order of links. This figure in the middle is a subgraph rewriting rule. In this rule, the P is represented a wildcard that has one link connected to the I atom, and the unspecified number of links going out on the membrane, which are described star Z, star X. This left elemental graph is written to this elemental graph to the right side by this rule. So this P matches these A and B atoms. So the membrane is paired off, and the I atom is written to N atom. In hierarchical graph rewriting, we often want to clone subgraphs. Cloning of subgraph is a highly expected feature of high-level graph rewriting language. But to handling edges is not obvious. For example, we want to clone this subgraphs with B atoms. In LMNtal, which handles port graphs, the reality of A and C cannot be changed. We must somehow splice 2 clones of the subgraph into the context of the original subgraph. In original LMNtal, the API named LMNtal for nonlinear membranes provides subgraph cloning constructs. The details are omitted, but this figure shows how copy token clone this membrane with P. However, we want to give a mathematical or logical background to this design. The design of graph cloning construct is highly non-trivial, even in algebraic approaches. A comparison of graph rewriting system with cloning constructs is shown in this table. Most frameworks adopt approaches based on category theory and distribution logic. However, we propose an approach that aligns with PL standard definition at the same time, we want to incorporate a mathematical or logical background. So our research question is, can we justify our language design based on some mathematical or logical system or design guideline? Now I move on to the explanation of MEL proofnets. Firstly, the definition of MEL formulas are as follows. The formulas allowed atomic formulas is negation, tensor, per, bang, and question. Tensor and per are called multiplicative, and bang and question are called exponential. Negation appears only in atomic formulas in the basic syntax. And otherwise, it moves or removed by the Morgan duality. Next, linear implication is defined by these formulas, and classical implication can be translated by using linear implication and bang. This figure shows the inference rule of MEL sequence. The definition is standard, so we omit it. But I'd like to point out that this promotion rule is important. It is known that the cut elimination theorem holds for MELL. MELL proofnets are graph representation of proofnets, proofs of MEL sequence with higher level of abstraction. For example, both left side and right side proof tree can be translated into the same proofnet. MEL proofnets are defined in two steps. The first step is the definition of graph structure named proof structures. The second step is the definition of geometric constraints on proof structure using switching graphs. Firstly, an MEL proof structure is a directed acyclic multigraph that combines the cells and wires and the promotion box. This promotion box corresponds to this promotion rule for sequent calculus. Next, MEL proofnets are defined by proof structure and switching. Please refer to the paper for detail. For example, this proof tree can be represented as this proofnet. The cut elimination rule for MEL proofnets are hierarchical graph rewriting. Hierarchical graph rewriting rules corresponding to those for MEL sequence calculus. For example, this bang-bang rule of MEL sequence calculus can be translated into this hierarchical graph rewriting rule. By using this rule, this left promotion box is moved into this right promotion box. Next, this is a bang contraction rule for MEL sequence calculus. This rule can be translated into this hierarchical graph rewriting rule. This rule involves a box cloning. This figure shows the simplification through multiple steps of cut elimination. This bottom left proofnet simplified to this bottom right proofnet. For MEL proofnet, the following properties holds cut elimination theorem, stability, confluence, and strong normalization. Now I move on to the design and implementation of the MEL API. We wish to establish a closer connection between LMNtal and MEL proofnets by providing LMNtal with well-motivated graph cloning and duration constructs inspired by MEL proofnet. Firstly, we define a new syntactic construct, process context aggregates. This construct represents a multiple copy of NI-P as process context. This number of copies is determined by the number of links represented by these bundles. So we can now represent an unspecified number of wildcards. Next, I'll explain the design and implementation of the API. We can describe clone and deletion using process context aggregates. For instance, the API named MELL copy clones this membrane with free links. The specification of MELL copy can be written in this graph structure. It is necessary to ensure the consistency of free links before and after cloning. This $A, $B, C1, and C2 are arguments introduced to ensure the consistency of free links. Firstly, I explain this X. When $P is cloned, X is also cloned. But to avoid the increasing free links, $P is with 2 ports are generated and each connected to cloned X and C1 or C2. Next, I'll explain this *Z. *Z is unspecified or number of free links. When $P is cloned, *Z are also cloned. So the number of free links is double. To ensure the total number of free links before and after cloning does not change. We can specify this structure with 3 ports to connect clone *Z to original *Z with process context. The process context aggregates are introduced to represent an unspecified number of $A. We implemented it as an API of LMNtal runtime. Now I move on to the explanation of encoding. Firstly, we show that MEL proofnets and their cut elimination rules can be directly encoded in LMNtal. By directly, I mean that each cut elimination rule encoded into one LMNtal rule. The encoding step is as follows. Firstly, the encoding of cells and wires are shown in this figure. The non-commutativity of input of tensor cell and power cell is represented by atoms, while the commutativity of the argument of AX and cut is represented using membranes. A contraction cell with commutativity input and a single output is represented by using both an atom and a membrane. The encoding of promotion box is shown in this figure. The outer frame of the box is represented by a membrane, and question gamma is represented by a bundle. And the blank white space is represented by a process context. So the MEL proof structure can be represented by a combination of cells, wires, and boxes. Next, we show that all 6 cut elimination rules of MEL proof nets can be directly encoded into LMNtal with the MEL API. We show the encoding of the following 3 rules in both non-trivial box operation as example. Firstly, we show the LMNtal encoding of Ban rule. The diagrammatic representation is shown in this figure, and textual representation is shown here. The only thing that has changed between the antecedent and consequent is the position of these braces. The migration of the box can be represented by the movement of the braces. Next, I show that LMNtal encoding of band contraction. The diagrammatic representation is shown in this figure, and textual representation is shown in this code. To encode this operation, 3 rules were necessary with NLMM API, but now it can be encoded with 1 rule using MEL copy API. Next, we constructed and visualized state space of determination. As an example, let's consider beta reduction of the simply typed lambda calculus. By the Curry-Howard isomorphism, the type derivation tree has a corresponding net, and its determination corresponds to beta reduction. In this example, there is only one reduction path of beta reduction. But we are interested in the state space of the determination of MEL proof nets, which correspond to this beta reduction. This state space is constructed and visualized using LMNtal runtime with the MEL API. In this example, we can see many reduction paths of determination. Also, by observing this state space, we can confirm well-known properties such as Church-Rosser and strong normalization. And we also can confirm non-trivial properties such as the existence of redundant paths like this. Next, we try to add rules have been proposed in the literature, and we can readily observe changes in the state space. For example, this rule, which pushes the weakening node, is used in the expression of substitution. But if we make unrestricted use on this rule, confluence is lost, as I show in the next slide. This space or the added rule in the previous slide is shown in this figure. The number of final states increasing to 4, so confluence was lost. In conclusion, rules could be easily added, and consequence of rule addition could be visually confirmed. So, LMNtal with the MEL API is useful as a workbench for proof nets. Next, we show that several process calculi can be encoded in LMNtal. For example, we encoded replication rule of the ambient calculus, where ambient are box structures that may be duplicated, migrated, and deleted. The encoding of this open rule is this LMNtal code. So, LMNtal using MEL is sufficiently general for modeling and computation. Our related work is as follows. Please refer to the paper for detail. In conclusion, we introduce MEL API, which is based on the determination rules of MEL proof nets, to perform cloning and deletion of hierarchical graphs in LMNtal. So I hope that this work will be as a beneficial bridges to both sides. Thank you for listening.
Any question or comment? Well, in the meantime, I have not a conceptual question, but more a contextual question. I wonder if the contribution of your paper is more on the design of this language LMNtal that is now more general and can do more things, or you think that your contribution can also be useful to the people that is working on MEL proof nets and can now use this language because it's better than the existing language to represent these proof nets?
Thank you for the question. I think that this contribution is in general useful for hierarchical graph writing.
So in other words, the resulting language, this LMNtal language extended to deal with these proof nets, is competitive with existing languages for proof nets?
Well,
if there are such languages, I don't know.